Okay, topic 7, we're going to look at a mains power supply, and it's something we'll actually go on to again next year, but we'll understand a basic power supply, so we're going to need to understand a half wave and a full wave rectifier. We'll also look at the waveforms that we get in the various parts of the power supply, and we'll need to look at ripple voltage and converting between RMS and P. So we're going to start off with our AC source. This is usually our mains voltage at 50 Hertz and 240 volts RMS. We'll talk about the RMS a bit later on. That's then going to feed into a transformer so that we can step down the voltage to some lower supply that's more useful for us. I'm not going to go through transformer theory, but primary coils, secondary coils, number of coils in the secondary is obviously going to be less than the ones in the primary to get a step down transformer. And then we're going to go into our rectifier, and that gives us then some rough DC, so that's the rectifier is therefore responsible for getting all of the current going in the same direction, and then it needs then some sort of smoothing after that, and then we have our output device that we're going to connect to it, so we'll call that a load. And that's a rough power supply, and this would be a block diagram for an unstabilized power supply. So we're going to start off with our rectifiers, and we're going to start off with our single diode to make a half wave rectifier. A nice simple circuit, and comes up quite a few times in electronics. So there we have the circuit, and all we're going to do is we're going to have a look at the signal there that we've got across our resistor. So there I've drawn my input supply. So when the input starts to go positive and we get greater than 0.7 of a volt, if we're using a silicon diode, then it will start to conduct. So we'll get an output just less than the input signal. And then as it starts going down, it'll go down like so. But then when the negative cycle goes through, so there's our positive cycle going through that way, but when it goes negative cycle there, negative, our diode will be in reverse bias, so nothing will happen then until we get our next positive cycle coming through. So we do have all the currents now going in the same direction. However, it's not very efficient because for half of the cycle we're not getting anything out, and like I said, because we need that 0.7 of a volt to get the diode to conduct, therefore the difference between the original input supply and our voltage across our output, there is going to be 0.7 of a volt difference. There we are, so we just made a note of that. Okay, let's go on to our full wave rectifier, so we need to be able to draw one. So the easiest thing to do with our full wave rectifier is to draw a square, and then you attach your supply to the top and bottom, like so. And then all we have to do then is put 4 diodes in, all facing exactly the same direction, top and bottom. So you'll actually see this drawn as a diamond shape on circuit diagrams, but it's far easier to draw it here as a square. So connections to your AC supply, top and bottom, and then your 4 diodes. And then all we need to do then is connect on the sides. They're going to take our output that we'll call across our load resistor. Now this isn't our actual load, it's not our output device, it's just what we're calling as load resistor because we need to have a resistor there so that we can complete our circuit. Okay, so if we draw what we've got on our output now, so if we look at our positive cycle, here this is going positive, so therefore our positive cycle we're going to conduct through this diode, around through our load, and back round to here. Now our current won't go through this diode because current to flow is flow from a greater potential to a lesser potential. Now it's already gone through one diode here, so it's going to be lesser potential, so therefore then the current then flows it back down through this diode and back round. So what we get then is that we get an output waveform like so, but this time round the difference being, as it's gone through two diodes, it's 1.4 volts difference. Now if we take when the waveform is going negative, now if this point here is going negative, then this point here must be going positive, must be positive with respect to this point. So therefore then current will then, for a negative cycle, will flow through this diode and round, and back round there like so. So therefore when we get our negative cycle, so we get it there conducting like so. So there we have a series of humps. Like I say, you've got to remember it is 1.4 volts less because of the two diodes. Okay, so this will be a good time to talk about RMS and peak. Now, most power supplies are quoted with the RMS value. However, for us to do any calculations, we need to convert that RMS value into peak. Now, what is RMS? Well, RMS is root mean squared, so it's the averaged voltage that would be equivalent to a DC supply. Yeah. So when we've got our mains voltage, that's actually 240 volts RMS. So what is the peak value? It's pretty simple for us to convert between peak and RMS. So the voltage peak equals the voltage RMS times by root 2. In general, if you're converting from RMS to peak, then your peak value should be a lot bigger than your RMS value. So if we take our 240 volts RMS, then that works out to be about 339 volts peak. So if we take a typical example where we've got to convert our RMS from our transformer into a peak voltage, so we can do some calculations to say what output voltage we got from our rectifier. So remembering to write down the equation first. So we've got 7.35 volts times by root 2. Should be expecting a larger value, and we've got 10.4 volts out. If we then follow that on with saying, okay, we've got a full wave rectifier connected to our transformer, so what's the output voltage? So we've got to take into account the two diodes, so we've got our 10.4 minus the 1.4 volts, because there's two diodes, so that equals 9 volts output. If it's only been a half-wave rectifier, then we've only had to take away 0.7 of a volt. So now that we've got all of our current flowing in the same direction, but we've got all of those humps, I think if we connect any circuit to it, we'd want to smooth it out. So most of the time we're going to use an electrolytic capacitor, and the capacitor will charge up to it while the voltage is rising, and then it will discharge while the hump falls, trying to keep then the output at a constant level. But depending on the size of resistor that we've got, and the size of the capacitor, then it will depend on the ripple that remains. So if we take our output from a half-wave rectifier, then our capacitor is going to be charging up during this point here, so we'll come back to that in a minute, and then just here, we're going to be discharging down, and then as soon as we get to here, the capacitor charges back up again and discharges down. We end up with a cycle that looks like that. At this point here, from there to there, that's our ripple voltage, remembering that the peaks that we've got are going to be 0.7 of a volt lower than our original supply voltage that we would have had. We'll just draw that with a same thing again with a full wave rectifier. So you can see that we've got the cycles twice as often now, so therefore hopefully we shouldn't have quite so much of a ripple because the capacitor hasn't got quite as long time to discharge down. So we end up like that. So we do have a smaller ripple voltage because we've got double ripple frequency. That's because our humps are happening twice as often as they would originally happening each cycle, but twice as many cycles in the same time as before. That leads us to the formula to calculate the ripple voltage. So we've got our current in our load, IL. We've got FR is our ripple frequency. And our capacitor C. And remembering that it's going to be double if we've got a full wave rectifier compared to a half wave rectifier. So one of the questions that we might be asked is, how do we reduce the ripple frequency? Well, we can just take into factors with the equation. So if we made the value of capacitor there bigger, then we reduce the ripple voltage. If we made it a full wave rectifier rather than a half wave rectifier, so we effectively increase the frequency. And therefore, and also if we put a larger load value on, so that we made the current a lot smaller, therefore then we reduce the ripple voltage. Okay, so there we have it. Let's just go back to these waveforms again. So if I was looking at this, so if we had a small current, then we wouldn't drop by very much, whereas if we had a larger current, then this would be dropping right down here. Okay, and the same type of idea would apply on our full wave rectifier, but to the same extent. Okay, let's do a couple of example questions looking at the ripple voltage and putting some of the other things together as well. Okay, so we've got this circuit here, 1500 microfarads, we've got 200 milliamps flowing through our load, and we've got 4.5 volts RMS. So the first thing we want to do is calculate what the ripple voltage is. So 200 milliamps divided by, oh, I should have said it's 50 hertz there. So therefore, that was 50 hertz. So then that's, because we've gone for a full wave rectifier, we're now at 100 hertz times by our 1500 microfarads. This is a ripple voltage of 1.33 volts. Okay. So let's have a look at what our maximum and minimum output voltage is now that we know what our ripple voltage is. We need to go back and look at converting our RMS to peak. So first of all, we need to work out what the peak voltage from our source or it might be from our transformers, but in this case it's just our source. So we've got 4.5 volts times by root 2 equals 6.36 volts. Okay, and now we need to take into account what we've got from our diode. So our maximum voltage that what we're going to have is 6.36 volts minus the 1.4 volts, because this is a full wave rectifier, equals 4.96 volts. Now we can use that 4.96 to work out what our minimum voltage is, because our minimum voltage is going to be our maximum voltage minus our ripple. So we're going to have our 4.96 minus our original 1.33 volts that we've worked out for our ripple, gives us 3.6 volts output. So our maximum voltage we're going to have across our load, almost 5 volts, and just a fraction above 3.5 volts. Okay, right, one last example then. Okay, so 15 volts RMS, full wave rectifier again. I think a lot much like full wave rectifiers. So our peak voltage that we've got equals our voltage RMS times by root 2 equals 15 times by root 2 equals 21.2 volts. So maximum voltage from a power supply runs through 2 diodes. 21.2 minus the 1.4 gives us just shy of 20 volts output. Okay, let's finish off with a ripple voltage. So let's connect a 100 ohm load and a 4700 microfarad capacitor to that. Okay, so first thing we need to know is what is going to be our current in our load. So current is equal to voltage divided by resistance. So we've just worked out that we've got a maximum of 19.8 volts with 100 ohms. Gives us 198 milliamps. So therefore our ripple voltage (198 milliamps). We assume it's a 50 hertz supply again, so that gives us a 100 hertz frequency times by our 4700 microfarads equals a bit better, but still not brilliant. Ripple 421 millivolts.